Hi, again, my name is Miguel Calles. I'm here to share some lessons learned, costly ones from serverless computing. So first, I'd like to start with sharing who we are and a little bit about our serverless journey. So Veritol is a startup in the tolling and transportation industry. We believe in bringing innovation to the industry by leveraging mobile, crowdsourced, and cloud-based technologies. In order to bring this innovation to the industry, we also need innovative technologies. And that's how we landed on serverless. With serverless, we're allowed to focus on application development and develop rapidly and deploy rapidly. We can do it with less infrastructure than typically done with server-based approach. We can also reduce our maintenance overhead throughout the software development lifecycle. And if properly designed, we can lower our costs as well. So some of you may be wondering what serverless is. Serverless is a technology that allows you to deploy applications without having to manage the server. Some wonder, well, how can you have technology without a server? And I agree, there's got to be a server somewhere within the technology stack, but the point is, we don't have to provision it. We don't have to configure it. We don't have to manage it. We don't have to secure it. There's underlying technology there that we just need to upload our function code or configuration, and we can then focus on developing the application, putting all the pieces together. So it makes development a lot quicker. So just to give you an idea of what serverless looks like, we built Auditol, one of our platforms, using Amazon Web Services. So we have a serverless website and a serverless backend. So for the website, we're leveraging three major services on AWS: Route 53 for domain name service, DNS, S3 for hosting or object storage, and CloudFront for a content delivery network, or CDN. So what happens when a user goes to our web application, auditol.io, Route 53 resolves that to an IP address. That IP address then gets redirected to CloudFront that does CDN. If the desired content has already been cached at the edge, then it just serves that cached content really quickly back to the web app. In the event that it's not cached, it goes to S3, obtains the content, and then serves it back to the web application. Now, our website also needs a backend, and our mobile app uses a backend as well. We do this by leveraging three other AWS services: API Gateway for defining API endpoints using the RESTful designs, Lambda for serverless functions, and DynamoDB for serverless database tables. So what happens when the mobile app or the website need to get data from the backend? They make an API call that gets sent to API Gateway. API Gateway will then forward that request event to a Lambda function. The function will process the event and do what it needs to. It may need to read or write to a database and send data back. So once it does its execution, it sends the data back to the gateway, and the gateway sends it back to the mobile app or website. So hopefully this gives you a feel for what serverless looks like and how a typical serverless design is implemented. So here's the bulk of the talk. I'll share some lessons learned. So there's going to be a structure to this. We're going to have a category and describe the scenario, the lesson we learned, the remediation we put in place to address our finding, and conclude with some risk and mitigations you can take away to avoid similar scenarios. The first category is inputs. OWASP serverless top 10 identified input injection as the #1 top security risk. So in this scenario, what we had is we had an API endpoint that sends data to a Lambda function, and it reads from a database. And we found that this database changes very infrequently, so it doesn't change very often. We implemented API Gateway Cache so that once the API request comes, it the gateway can serve it right back, similar to what a CDN does. That way it doesn't ever have to do a Lambda function call and a database read for most situations. But there were times when the database did get updated, and we don't want to serve old cache data. So we had a different process in place where when the database is updated, it would send an update event to a Lambda function. The Lambda function will then say, oh, I got an update. I'm gonna send a request to the API gateway and have it clear its cache. Seems pretty straightforward, right? What we found was that there was accidental injection attacks that we weren't expecting. For whatever reason, sometimes AWS would send the Lambda function old events. So the table had not been updated recently, but yet it was still sending old events the Lambda function that should have not happened. So the function was saying, oh, I got an event, send a clear cache request to the gateway. Oh, I got another one, clear cache, clear cache. It was happening so many times in a very short period of time. And the API gateway ended up getting so overwhelmed that said, I'm not accepting any more requests. And even from API endpoints over HTTP using the RESTful protocol, ended up turning into a self-induced denial of service attack. Yikes. So we had some outages that we were not planning. So to remediate this, what we ended up putting in place was we had the function do input validation according to the number one risk recommendation to mitigate that. So they only processed the newest events. We also had the Lambda function keep track of when the last cache clearing happened and limit it to every 5 minutes, so that you can only clear the cache once every 5 minutes to avoid overwhelming the API gateway. So this kind of describes how you can avoid input injection attacks, even accidental ones. Just as a side note, we ended up determining that the database only gets updated during the release process based on some configuration parameters and build specific changes. So we went away from this paradigm that we have here in the diagram and started using serverless plugins. And when there was a release in the CI/CD pipeline, the serverless plugin would make the API call to the gateway and say, clear the cache, because the database was being updated at that time during the release. So we mentioned some of the risks. So code injection, it could be SQL commands, AWS commands, GraphQL, if you're using like the AppSync service, there's a nested recursive attack. This really awesome demo from OWASP, AppSec Cali 2019, that shows that demo, how it turned into like a couple-minute long execution and at 1,000 times. It ended up being several $1,000 cost. So regular expression attacks, and if there's a bad input, it could result in unexpected 500 error if not planned properly. So to mitigate, make sure you always validate your inputs, do safe to deserialize your inputs like JSON, and make sure you have safe regular expressions. If in the event there is a code injection attack that makes it through, make sure you have the lowest identity and access management privileges so that it cannot execute any unintended functions. Take advantage of great tools that are built into IDEs or as plugins, put them into the CI/CD pipeline to do linting and static code analysis, and take advantage of try-catch blocks so you can exit gracefully when a bad input makes it through. So the next one is on rate limiting. Typical for most multi-factor two-step verification, we had implemented a mobile app for client. So user needed to log in, it sent the API request to the gateway, then it gets sent to the function then verifies the username and password against the identity provider. Awesome. If it's successful, the identity provider sends a 2-digit code via SMS to the phone. The user then entered the 6-digit code, sent the API request, function verifies against the identity provider. Cool, all successful, the user is logged in and gets a JSON web token back to have the session on the application. Well, we found during penetration testing that the process, the business logic looks good, but there was a unexpected flaw in the design, someone could do a brute force attack, try a million codes, and bypass the two-step verification. Yikes. So what we did to remedy this is we did a rate limiting at the API gateway, so only a certain number of requests can make it through in any given minute, and also do lockouts. If it failed, let's say after 3 failed attempts, either the username and password or the verification code, then it would do a lockout and you couldn't log in for, do another attempt for a period of time. We also decided to do a moving target. If in the event that the incorrect code was sent, it would then send another 6-digit code, so that there's always a moving target. You couldn't just try to get the same code. By not having rate limiting, your application could be vulnerable to brute force attacks, bot scraping, or analyzing your application, and various denial of service attacks. And the costly part is you could have a cost spike that could increase your costs. And if it's an extended period of time, it can be very costly. So the way to help mitigate against these things is to have web application firewalls. You can put a WAF in front of your web application and also in front of the API to help reduce brute forcing, bots, denial of service attacks. Also wanted to mention that you should be monitoring usage, errors, and all, just understanding what your application is doing and your billing, so that you can know when something anomalous is happening. You can address it right away and avoid a surprise bill later on. All right, so over provisioning, just for simplicity and just to keep the configuration on our serverless framework file looking clean, we had defaulted to default a compute size, default timeouts, and set a standard read-write provision for the database. Well, what we found was if sometimes bugs sneak into releases, and when they go live, all of a sudden you have all these errors popping up, and it could be many errors being realized. And if you have the maximum compute and the maximum timeout, well, you're going to be paying for all that execution time. And it gets more expensive the longer and the bigger the compute size is. And same thing with provision read-write capacity. If you, just for simplicity, make it a big amount of provision, then well, you're going to be paying for that while it's happening. So that can get really costly as well. So to remedy these situations, we understood how each function executes and try to optimize it. So sometimes having low memory or low CPU is fine if the function does very simple things, but sometimes it's better to pay for more compute and memory when if the function is intensive. So if, maybe more costly at the compute side, but the execution time is smaller, and so it kind of offsets and ends up being more cost efficient. Then also understanding how long a function typically executes, and then understanding how long, what's the maximum time it should need before it times out. Sometimes you can do it during unit testing or integration testing that insert bogus or erroneous inputs to see how the functions execute with an error. So then that way you can, if a function typically takes 2 seconds, maybe you could cap it off 4 seconds. So that's usually the longest it would need to execute for an error. For a database, we decided to move to on-demand. We had very spiky traffic, so there was no need to have constant provision resources, read-write. So the having to pay more per write and read request ended up being more cost efficient, and then having a dedicated amount. Something to keep in mind though, with if you're not doing rate limiting on your functions that read and write against the database, a cost spike or an attack could be expensive. So it's something that just tying it back to rate limiting, that's a mitigation for on-demand database read and write capacity units. So we talked about the risks. For just mitigations, understand how your application functions and size it appropriately. So for over-privileged policies, again, this is a risk in the serverless top 10. So what we're doing, again, just developer simplicity, all the required IAM privileges for every function were put in the default role. And so what that resulted is functions were now being given overly permissive policies. They were allowed to do things that we're not supposed to do. So for example, this one function is meant to just read a database, but we found that it could do something like modify the IAM password policy. So you see on the left side of the function, there's a overly permissive policy there. I made it admin just to get the point across that if you have overly permissive or admin privileges, some bad things can happen. So what we did is we crafted some malicious intent, a remote execution attack. We were able to successfully modify the IAM password policies. That's not good. So what we decided to do was to stop using the default role and do one IAM role per function so that the policy was limited to what it was done. So you see the change on the left-hand side in the JSON that this function is only allowed to query, and it's only allowed to query a specific table. So that way, when we tried the malicious remote execution attack again, we were not able to modify the IAM password policy. So the risk of having over permissive, over privileged policies and roles is that a malicious actor can do execution attacks, do lateral movements throughout your AWS infrastructure, could lead to account takeovers and data leakage. I believe the Capital One breach from a couple of years ago was a result of over permissive IAM policies. So we mentioned I mentioned the remediations. Those are mitigations you can put in place. I highly encourage leveraging temporary credentials. AWS has a service called Security Token Service where it could issue a limited lifetime credentials. So rather than having an access key that lives on forever until revoked, and it's set, let's say, to has wildcards all over its policy. You can just do, if you can, least privilege, but even if it's admin or very permissive, it's short-lived, like 15 minutes. That way, in your CI/CD pipeline and even on your own developer machine, you can keep the policy short-lived, active, short-lived. Another thing we found that was really costly was failure, not keeping track of AWS service outages and failures in our application. As great as these cloud providers can be, they do experience outages. And so if we're not aware that there's an outage and we're not keeping track of, let's say, 500 errors as a result of an outage or 500 errors as a result of a bot attack, it can have cost implications. It could affect, result in data loss. In one of our client applications, we found that it was an AWS outage for over an hour, and we were losing pricing data, so we couldn't bill our customers accurately, and that's bad. That's not good. So we started monitoring when AWS went down, do some internal monitoring as well to see if we can detect it before AWS reports it officially, keeping track of when 500 errors, and we started exploring multi-region design. So if, let's say, North Virginia was down in AWS and Ohio was functioning, our application can still keep running. That comes in handy when so related to multi-region, you can do multi-cloud designs as well. Summer of 2020, Azure had an outage in every region, I think, for an hour or two. And so if your application was solely hosted on Azure, your application would be down completely. But let's say if you had designed it so that it can run on Google Cloud and also on AWS, then your application can still be running, maybe in a degraded state, but it'd still be up. So some of the risks that we mentioned, we experienced data loss. An attacker can use 500 messages for reconnaissance. So if we're not tracking that there are spikes in 500 messages, we may not realize that our application's being investigated. But I just recommend using monitoring and alerting to be aware that this is happening. And for your clients, leverage local storage. The web browsers and mobile apps have local storage and session storage and secure storage. You can put your data there first and then make the API call. And if the API call fails, it'll still be stored locally so that the next time the service is back up, you can try again to write the data. Lastly, I want to conclude with cost engineering. So cost engineering is the exercise of understanding your costs, understanding how your application works, and how you can keep your application functioning as efficiently as possible with the lowest amount of cost. So it's related to many of the things we've already presented earlier. So in this example, we launched a serverless application and it went operational. And as we started adding more customers, we started seeing slight cost increase, and then noticed the cost was increasing significantly by June of that year. And by the time we started thinking about doing something about it, it was July. So our peak, this is relative cost, so the peak is in June, and that's the highest cost. And so we decided to understand what how our application was designed and how we can keep our costs low. So we started doing a cost engineering exercise in July, and by August, we started seeing lower costs, and we kept continuing to do that over 2 to 3 months, and by October, we were at 98% of the cost from the peak in June. So we found this to be very powerful, that we didn't have to change very much in our application. Just with some optimization, we can still have the same level, same design and same level of quality for application, but at 98% of our cost. And that's huge. That can be a game changer, especially if you're trying to run lean and mean. So just as mentioned, it can be expensive and cost. By not doing cost engineering, you may be paying for more than what you need to. So some things you can do to help with cost engineering is to do price analysis. There may be some services that are similar enough, either within the same cloud provider or across different cloud providers, and one may be cheaper and still provide the same benefits and may still meet your requirements. So you can just choose the less expensive one. Recommend doing stress tests on your system before making it live, putting it into production. That way you can see how your system reacts when it's under a load, and you can catch potential cost spikes in advance and actually potentially mitigate them ahead of time before they even happen. And as mentioned before, just monitor your application, monitor your costs, make sure you understand how it's operating so you can catch anomalies. So in the spirit of 20th anniversary, we want to think, what is Veritol trying to achieve for the next 20 years in the tolling industry, and how do we do that securely? So our goal is to reduce the total cost to collect for a toll operator, so that they have to only spend a few cents to collect their tolls costs from customers. And so we believe we can do that through cloud computing, especially serverless technologies. Serverless allows us to scale up very quickly, and as you saw from cost engineering, we can aim to keep costs much lower, which we can then pass on to our customers and allow the tolling agencies, the tolling operators, to pass on their cost savings onto their customers as well, maybe in the form of a lower toll payments. We also want to provide a way, a secure way, to people to work off their tolls so that they can use mobile apps and cloud-based services to earn income to help offset their toll costs, giving them opportunities maybe for a better job that's further away from where they live. So as you may wonder, there's going to be a lot of transactions, a lot of processing in the cloud. There's going to be sensitive data like license plates, names, addresses, billing information, GPS data. And so we believe we can do that at scale with serverless and also do it securely by leveraging proper cloud security principles. So there's many resources out there for those of you interested in serverless and serverless security. OWASP has the top 10. The Cloud Security Alliance has their top 12. There's many good blog posts on serverless best practices, serverless security. There are books on serverless from Apress and O'Reilly, and there's the cloud provider documentation. I find it really helpful. I read through that a lot because they, in many of their configuration guides, have sections for how do you configure it, how do you do a proper architecture, and even some security things you keep in mind. And there's GitHub repositories also that have compilations of serverless content as well. I noted one of them here. So I'd love to hear from you. I'll be on the Slack channel to answer any questions, but do contact me via email and LinkedIn. And I am a published author, and I do write and post content on my blog, so check out my site. Thank you so much. I hope you found this presentation helpful. And I just want to share that Apress has agreed to do a book giveaway for serverless security. So if you're interested, go to my website, go to the OWASP 20 address and enter your email for a chance to win. Thanks again.